Welcome to the Math Tutor on the topic of logarithms. In our study of calculus and pre-calculus, trigonometry, and algebra and all these things, I've been stressing over and over again the importance of understanding opposites. Opposite of addition is subtraction, opposite of multiplication is division, opposite of squaring something is taking the square root of something. And those are useful in solving equations. Okay, very, very useful because you need to know the opposite. Here I'm going to teach you the opposite of the exponential, which we've looked at in the previous section. The opposite of an exponential is a logarithm. The opposite of a logarithm is an exponential. So as you might guess, they're going to be very useful in solving equations of certain types. So we need to understand them. And in this section, I'm going to introduce the logarithm, plot it. We'll talk about some very important properties that you'll need to basically memorize because they're very important. And we'll go from there. So let's just dive right on into it. I'm going to give you a little primer on the subject material here, and then we'll go ahead and do some problems. If I have something that looks like this, y is equal to the logarithm, and I'm going to say it is the logarithm to the base a, it's a base, of the number x. What does that mean? You may see this in books, you will see this in books. Every logarithm has what's called a base. That's written as a subscript here, and the base in this case is a. You're also taking the logarithm of a number. In this case, you're taking the logarithm of x. So the logarithm of x with regard to the base a, you put that in a calculator or a computer, you'll get a number, and I'm just saying that that's equal to y. What that means is the following. How do you figure out the answer? This is the following. A to the y power equals x. This is a definition. This is something that you just can't derive. This is something that you look at in a book and it's circled and you have to understand it and you have to basically use it and memorize it. This is a definition. I told you that logarithms and exponentials were opposites, and this is why they're opposite. You have a logarithm, you have a base a, and you're doing it to a number x. How these things relate to each other is whatever this quantity is equal to over here, if you take the base a and raise it to whatever this number equals, you will get the number that you took the log of in the first place. So if you're trying to take, like on a calculator, you have that log button. So if you put a 2 in there and you take log 2, well, it's understood that the implied base is base 10 there. Okay? It's a base 10 there. So what the calculator is going to do is it's going to try to figure out the following. It's going to say, okay, 10 to the what power, and I just put a question mark here, equals 2. Okay? You know, that's really tough to do. So why don't we change it and say the problem is log base 10 of 100. Okay? So it's going to say 10 to the what power is equal to 100. Well, you should be able to figure that out in your head. The question mark is going to equal 2 because 10 squared is 100. So if you take 100 and you press the log button, which is implied a base 10 there, okay, it's going to put a 2 there because 10 to the what power equals this? Well, that's 2. And that's what I mean here. A to the y power equals x. That's what this relation means here in the big picture of things. I've already mentioned that logarithms and exponentials are opposites of each other. Okay, so if you think about it, and what I mean by opposites, what I mean is like if you have the square root of x and you square that quantity, which is the square root of x, all you're going to get back is x. Because you have a square root and you're squaring that, and so they kind of cancel. Or if you have, 3 plus x minus x, that's just going to equal 3. You can add an x, subtract an x. You can do the opposite here, and you kind of get rid of x altogether, and you just have what's left over. I'm going to give you another example based on the fact that log and exponential are opposites of each other. Okay? If you have a to the y equals x, which is what we had here, I just told you that that was sort of how it's related to the logarithm. Then if you think about it, a to the y, which is this, log of the base a to the quantity x, operated on the quantity x, all that you're going to get back from this is x. This looks kind of confusing, but really all I'm saying in a nutshell is, just like you have a square root of x and you square it, those are opposites, so all you get back is what's on the inside because the rest kind of just cancels like this. If you have some number and you raise it to the logarithm of x to the same base that you raised it to, well then it's like the logarithm kind of just cancels with the a because they're opposites, and all you're left with is x. You'll find that that's useful later on when we start solving equations, because maybe I give you an equation that has x tied up in an exponent somewhere on an exponential. And how do you get x out of the way and free up x? Well, the only way you can do it is to use a logarithm, because a number raised to a logarithm, if it's the same base, you just get back what you had there in the beginning. So that's a property you might want to put in your back pocket. We're going to work on some problems, and you're going to see us use that. Let's go ahead and go over some more properties, and then we'll work those problems. Knowing what we know about logarithms, if I write log base a of the number a, where a is the same thing. Okay, so the example of this would be like log of log base 10 of the number 10. What would that equal to? Well, what I'm trying to do here is a to the power of what equals a. This is exactly what I have here. A to the power of what equals whatever it was I was looking for. A to the power of what equals whatever it is I'm looking for. Well, it turns out that the question mark is just equal to 1. Okay? That makes sense. Okay? What if I had log base a of the number 1? Then how would I find that? Again, you start the same place. And I'm trying to give you the thought process that I use. When I look at a logarithm, the first thing I look at is the base. And I say, I think it exactly like this. Base raised to what power equals the number over here. And that's how you figure out what this logarithm is going to equal. Okay? Well, a is just some number. Raised to what power will give you 1? Well, anything raised to the 0 power gives you 1. So a to the 0 power gives you 1. So the answer to that would be 0. So if you type in 1 and take the logarithm in your calculator, you're going to get 0. Okay? So those are kind of some basic properties. Here are some more different, interesting properties that are going to become very useful. You might want to either write them down now as I go over them on the board, or if you have an algebra book or a calculus book or something handy, or a pre-calculus book, crack it open to that page that deals with logarithms, and don't read the book, listen to me, but it'll have some of the stuff written down so you don't have to write it down. This is a very important property that we're going to talk about here. Log base a of u times w, which is just two numbers multiplied together, or two variables multiplied together, equals log base a of u plus log base a w. Okay? What I'm trying to say is, if you're trying to take a logarithm of something, and this something is two things multiplied together, all it is the log of the first one plus the log of the second one. So if these were two variables, x and y, it'd be log of x plus log of y, if they're multiplied together in there, just like this. So this is, very important. Remember this. Likewise, you'll see some symmetry here. Log base a of u divided by w, where u and w are just numbers, letters, whatever, is log, again, base a, it's all going to be base a, which is just a number, u minus log base a w. Okay? So you can see the symmetry. If you're taking the log of two things that are multiplied together, all you do is you take the log of each thing individually and add them up. If you're taking the log of two things that are divided by each other, all you do is you take the log of the top and the log of the bottom and you subtract them. So you've got some symmetry here. The final one, and again, that's a very important one you're going to use all the time. The log base a, of course, of something raised to the power. This could be x squared, x cubed, it could be 3 to the x, it could be anything raised to a power, is going to be equal to this exponential, c, that you had in here, times the log, again, base a as always, of u. Okay? So these are three very important results. You might want to pause the video and maybe write these down, or if you already have them written down, great, continue on. But basically you have the three things. If you're taking the log of two things multiplied, then you take the logs and you add them up. If you're dividing two things and you're trying to take the log, you take the log and you subtract them. And if you have an exponent here, you just pull the exponent out of the log, and then you're left with log of u. I'm not proving any of these. You're just going to have to believe these. These are things that you can look up in books that are derived in great detail, probably derived using calculus, believe it or not, but it's not in our interest here today to spend 5 or 6 boards of boring stuff to prove to you why these are true, but we're going to use these today. Finally, I just wanted to point out, because we talked in the previous section about the letter E and why it's important. If the base is E, which is what I told you almost always is going to be that, because base E is a very important deal, then this log to the base E, okay, instead of writing log base E like this, it has a special symbol, ln. Okay, so instead of writing log base E of whatever, you would write ln of whatever. This ln stands for natural logarithm, because you'll find that natural logarithms with the base E and exponents with the base E, they're all over the place in nature, and population growth, bacteria, any number of different places where it pops up. Anytime you just have log of something without a base written there, okay, implicitly, it's a base 10 implied. I'm just trying to tell you some things to kind of shortcut you so you're not scratching your head. So we've always put base A, base A, base A, base A. Okay? If you don't write it down, it is implied it's base 10. If you mean to have a base E, you should write ln down. That's kind of the accepted deal. Okay? So let's move on. After we've talked about this, let's work a few problems that use some of those properties. Okay? First set of problems is going to be this. 4 to the cube to the third power equals 64. Question is, write this equation in log form. Okay? We've already talked, before about how to do that, and so now we're going to do that here. And I'm just going to write it down and we're going to talk about it. What this means is log base 4 of 64 would equal 3. Okay? I'm changing this into log form. And remember, I told you, every time I see a log, I go start at the base. This to the what power over on the other side of the equal sign equals 64. 4 to the third power equals 64. 4 to the third power equals 64. These two things are equivalent. Log base 4 of 64 equals 3. It's equivalent to 4 to the third power equals 64. Okay? What if you had 10 to the minus 3 equals 0.001? Okay? First, you've got to start at the base. That would be log base 10 of 0.001 equals negative 3. Why is this true? Because I start at the base. 10 to the minus third power equals 0.001. And if you think about it, 10 to the minus 3 equals 1 over 10 to the 3 equals 1 over 1,000. And so that's equal to this. So what you do is you just sort of figure out what goes where to kind of match it up with the logarithm form. And similarly, we can start with the log form. We can go to the exponent form. Log base 10 of 1,000 equals 3. We've kind of already talked about that, but that would be starting at the base. 10 to the third power equals 1,000. And you can see that that's true, so that makes absolute sense. These two are different equations, different relations, I should say, and they're both true. Okay? And if you have something more abstract, you could say log to the base t, which is just some number, of the number r equals p. Again, start at the base. t to the p power equals r, which is this. So you start the base, raise it to whatever it's equal to, equals that. That's how you solve logarithms. Not very intuitive, I must admit, but that's just the truth. Let's try to solve a few equations with logarithms. See if we can understand why this stuff's important. What if I had log base 3 of x minus 4 equals 2? Okay, how would I solve that problem? Now this is a problem you can't tackle at all just with regular algebra because you've got a logarithm, you've got this weird base, you're trying to solve for x, but you don't know how exactly to get x by itself. You can't add or subtract, multiply or divide anything, or take a square root or anything like that to get x by itself. And so we need to figure out how to do that. Well, one thing I did tell you is that the opposite of a log is an exponent. An exponential, I should say. So how do we use that? Well, if you start at the base, just like we did before, 3 to the whatever power over here on the other side of the equal sign equals whatever's left over here, x minus 4. That's not that bad. Start at the base, raise it to the power over here equals this. 3 squared is 9 equals x minus 4. I'm going to move 4 over here, so x is just going to equal 13. Not too bad. Start at the base, go over here, equals this. That's what the log means. Log base 5 of x squared equals negative 2. Again, start at the base, 5 to the negative 2 power equals whatever's left over, x squared, right here. 5 to the negative 2 is 1 over 5 squared equals x squared. Because you can just, since it's a negative exponent, you can put it on the denominator. We can continue over here. 1 over 5 squared is 1 over 25 equals x squared. And of course, to solve for x, you take the square root of both sides. So x is going to equal plus or minus 1/5. Plus or minus square root of this side, square root of 1 is 1, square root of 25 is 5. So you'd have two answers, plus or minus 1/5. Okay, what if I had log base 6 of 2x minus 3 equals log base 6 12 minus log base 6 of 3. Okay, on the right-hand side of the equation, first of all, before I deal with the left, look at the right. What I notice on the right-hand side of the equation right away is that this is a difference of two logarithms that have the same base. So if you remember back on the previous board, I had written down that that would be equal to log 6 of 12 over 3. That we had said that if you have two things divided by each other in here, it's the same thing as taking the log of the top and subtracting the log of the bottom. So you just write it like that. So on the right-hand side, you're just going to have log base 6 of the number 4. Of course, you're still going to have what you had over here on the left to begin with. So I'm just going to write that again. Okay? Now I'm going to do something you probably have never seen before. I'm going to put both sides of the equation in the exponent of the number 6. So I'm going to write it like this. 2x minus 3, this is all in an exponent up here, equals 6 log base 6 of 4. There's a very, very good reason why I did that. The reason is the opposite of a log is an exponent when the same base is there. We had just talked about that before. And because I do this, because I put them both, I can do the same thing to both sides of the equation. It's legal as long as I do it to both sides. So I put this side in the exponent of the number 6, and I put this side on the exponent of the number 6. This will cancel with this, and this will cancel with this. So what I'll be left with is 2x minus 3, which is just what's left over here, equals 4. So 2x is equal to 7. I just moved that 3 over by adding it. And x is equal to 7 over 2. The only trick here, and this is really, really important actually, is when you have an x wrapped up inside a logarithm, you need to get it out in order to solve for the x. So you just raise it to whatever base, use the base that's in here and you put that in the exponent of that number. So if it were base 10, it would be 10 to the stuff. And then it cancels out because it's the opposite, just like we use all the time in algebra. We need to know the opposite, like with the square and a square root, to proceed. Now what if we also had a different equation that was more like log base 10 of x squared equals log base 10 of x? And how would that work there? Well, I can do the same thing. I can take, because the base is 10 and I want to get x by itself, I can put this on the left in the exponent, this whole thing in the exponent, and I can do the same thing here. Okay? And what I'm going to be left with is this log is going to cancel with this 10, this log is going to cancel with this 10. I'm going to be left with x squared equals x. So then I need to proceed as follows. I can just take this x squared, move this x over, and say that's equal to 0. I'm going to solve for x now. I'm going to factor out an x, pull an x out, x times x gives me x squared, x times negative 1 gives me negative x, and then I'm going to solve this, and you should know from algebra that x will either be 0, or I'll have also x minus 1 equals 0, so x will equal 1. Now, we have two solutions here, and you should always check to see if they make sense. Here's one solution, x is equal to 1. If I put x is equal to 1 here, 1 squared is 1, so I'll have log of 1 over here. If I put 1 over here, again, I'll have log of 1. So that makes sense, so this x equal 1 is a solution. Now let's check this one. At first glance, this looks like it's perfectly fine to do. If I put x is equal to 0 in here, if I put x is equal to 0 here, it'd be log of 0, and if I put x is equal to 0 over here, I'd also have log of 0. So it looks like that would work. But you'll find out that you cannot take the log of 0. It's undefined. And we'll talk about it in a minute when we get to the plot. But when you think about it, is log base 10 of 0. That's what we're testing out here. What would that mean? That would mean 10 to some number equals 0. I challenge you to find a number so that if I take 10, raise it to that number, it's going to equal 0. You can't do it. If you get, 10 to the second power is 100, 10 to the third is 1,000, 10 to the fourth is 10,000. Even 10 to the 0 is still equal to 1. Remember, anything to the 0 power is 1. If you start going negative, you'll have 10 to the negative 1, which is 1 over 10. Okay? And you'll have 1 over 100, 1 over 1,000, etc. as you go negative. There is no number that you can find. So if you were to take 0 and go to your calculator and try to take the logarithm, it'll give you an error because it won't be able to find it. So what you need to do is discard this solution and keep this one for this problem. It's a little bit unfair because we haven't actually plotted the logarithm function yet, but we're getting to it, and we're about to do that here in a moment. Before we do that, let's take another example. Log base a of quantity x squared y over z cubed, okay? And I want to say that I'm going to simplify this expression, okay? That's what we're going to try to do now. We're going to try to simplify this expression fully. Well, if you remember back from our identities, we had log of a times b is log a plus log b, okay, basically. So that's what I'm going to do here. This is what we have on the top, but also remember that we had the other expression. If you had a over b, if you're taking the log of something like that, that'd be log of a minus log of b. So you could go in any order you wanted, but I'm going to use this one first, okay, because I think it's easier. So I'm going to say this is going to be equal to log base a of x squared y minus log base a of z cubed. I'm just going to say that that's true. So I've used this guy. Great. Now I notice that this is a product of two items there. So I'm going to further expand this and say this is log base A of x squared plus log base A of y minus log base A z cubed. And you can see all I did here is I took this and I used this expression. Log of A times B is equal to log A plus log B, where A is equal to x squared and B is equal to basically y. And so I do this, and then I just kept this there at the end. Okay? The final little identity we need to use is recall if we have log of u to the c, where c is some exponent, that's just c times log of u. And we wrote those down on the previous page. You pull that exponent out, and you have log of u left over. I can do that right here. I'm going to make this 2 times the log base A of x plus log a to the y minus log a z cubed. So really it's fairly simple. First I noticed I had a division going on, so I subbed them out this way and noticed that I needed to subtract those logarithms. And then I noted I had a times b, and so I separated those two as using addition. And then I noticed I had an exponent, so I used this third one to pull that out like that. Finally, notice that you also have another exponent down here. And I'm going to do the same thing to it. 2 log a of x plus log a y minus, I've got an exponent here, so it's just going to be 3 times the log base A of z. And there's nothing else you can really do to that, okay, because you can't do anything here, your exponents are out. You can't do anything else here, your exponents are out. They're all different letters in there, so you really can't do anything more than that. So these little identities, we ended up using them all in that one example. They're pretty useful. They can definitely save you, okay? And that's why we study them, and that's why they're important to know. Now finally, we're going to go ahead and graph the logarithm function because it's important, just to kind of think about what it looks like. First thing I want to do is refresh your memory on the exponential function, because we'll find out in a minute the logarithm is just the opposite of that. Okay, so if this is the number 1, I think you will remember that the exponential function f of x equals a to the x is given by this. It goes through 1 and it goes up exponentially. This is f of x and this is x. Okay? What I'm going to show you is that if you draw a dotted line at 45 degrees here, like this, the logarithm function is going to look very, very similar. It's going to go through the point 1 here, okay, and it's going to come up from this axis and it's going to go like this, okay. So if you have the exponential function and you flip it over a line that's at 45 degrees here, you will arrive at the logarithm function. Log base A of the number x. So as you plug in numbers of x here into this formula, and you've defined what base you're working with, it could be base 10, base e, whatever, you're going to get a line that looks like this. The exact shape of that line is going to depend on the exact base you use, just like it does for the exponential. So it might bend a little bit down or a little bit up, but it's going to look essentially like this. So just remember that the logarithm is a mirror image of the exponential. And the reason that it goes through the point 1 here is pretty easily explained. If you take y is equal to log to the base A of 1, I'm trying to find out what y equals when I put 1 here, okay? Then what I will get is A to the what number equals 1. Remember, start at the base, to the what power equals 1. And I think you can convince yourself that your question mark should be 0, because anything to the 0 power gives me 1. So that's why it's there. Now I don't know about you, but logarithms I think can get a little bit confusing every now and then because it's not quite so easy to put your hands around. I mean, you've got a base and a number, and you're saying that this is defined by taking the base and raising it to something and saying it's equal to this. It's a little bit off-putting. I tried to work a few examples to kind of get you comfortable with it. I encourage you to continue working more examples in a textbook and go from there. But I can tell you that logs and exponentials are important. You need to be comfortable with them as we move out of here and into other topics. The next section of the class, we're going to solve equations that have logs and exponentials in them, and we'll get even more practice working with logs and exponentials, and we'll get even more comfortable in the next section.